Okay, this is part 2 of graphing rational functions. Rational functions are fraction functions. They have a numerator and a denominator. And so for this second part, we're going to look at horizontal and oblique asymptotes, finding x-intercepts perhaps, and finishing this off by graphing this. And we're continuing from the last, on the same worksheet from the last video, where we already talked about holes and vertical asymptotes and domain, and I think we found the y-intercepts on those. So right here, this is a very generic form of a rational function. A rational function is a polynomial divided by a polynomial. And so right here, the numerator is this polynomial, a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, and so on, over another polynomial, b sub m, x to the m, plus b sub m minus 1, x to the m minus 1, and so on. So this is a generic rational function. All right, why do I bring this up? Well, because the degree of the numerator and the degree of the denominator is really what we look at to determine horizontal asymptotes. So real quick, what is a horizontal asymptote? If you will recall with me this function, last time I looked at 1 over x. Let's look at something different. Let's look at this. 1 over x, let's see, plus 2. This, last time we looked at 1 over x, let's look at 1 over x plus 2. This plus 2 is a vertical shift. So we take this same function, this basic function, the reciprocal function, and shift it up 2 units. So we're going to go up 2 units, and that means that this is my new x-axis, and this is my new y-axis. So it's ended up being the same, and this is where I'm going to put this basic graph on here. This is what this looks like. This still has a vertical asymptote of x equals 0, because when x is 0, it'd be undefined. But this got shifted up too, so it has a new horizontal asymptote at y equals to 2 is the horizontal asymptote. What is the horizontal asymptote? Well, when x gets very, very big, at positive infinity, it gets close to whatever horizontal line this is. So in this case, it's y is 2. Or when x gets very, very big and negative, it gets close to a horizontal line. So this is y equals to 2. That's the horizontal asymptote. So that's what we mean by horizontal asymptotes. What's an oblique asymptote? That is when your graph does not hug a horizontal line when x gets very big and positive or very big and negative, but it hugs some line that is not horizontal but is at a slope. You might have a curve that does something like that. It hugs this as it gets very big, or does this. Oh, that's not going to do that. It's going to do something different. But anyway, it hugs a line at an angle. We'll see that when we graph one of these has an oblique. We'll see what that looks like. Okay, here we go. How do we find what the asymptotes are? We compare the degree of the numerator with the degree of the denominator for each function. The degree of the numerator is what I'm calling n. The degree of the denominator is what I'm calling m. So here are the rules. If the degree of the numerator is smaller than the degree of the denominator, if n is less than m, automatically we get a horizontal asymptote at y equals to 0. Automatically, y equals to 0 is the horizontal asymptote every single time. All right? What about when the degree of the numerator is equal to the degree of the denominator? We get a horizontal asymptote, y equals to a number, but what it equals to is the ratio of the leading coefficients. So if I look at my generic, I'm going to pull this first term out, r of x. I'm just going to make it easier to see. We've got a sub n, x to the n, plus some more terms, over b sub m, x to the m, plus some more terms. This is the leading coefficient. So in the case where the degree of the numerator and the denominator are the same, like we have an x squared over an x squared, or x to the 7th over x to the 7th, y equals to a sub n over b sub n. A sub n over b sub m is the horizontal asymptote that we get. All right? In the case where the degree of the numerator is bigger than the degree of the denominator, let's say that this was x to the 4th and this was x to the 3rd, or this was x to the 4th and this was x to the 2nd. Whenever the degree of the numerator is bigger than the denominator, then there's no There's no horizontal asymptote. There is a however case for the oblique we'll talk about in a minute. Okay, so let's go through here and say, hey, what's going on here? The degree of the numerator here is x to the 1. N is 1. The degree of the denominator is m is 2. Let me erase this other stuff. M is 2. And so in this case, n is smaller than m, so automatically y equals to 0 is the horizontal asymptote. Okay, that's the news for the horizontal oblique asymptotes. Right here, the degree of the numerator is 2, the degree of the denominator is 2. In this case, we're at right here, n is equal to m, so we get y is equal to the ratio of the leading coefficients. The leading coefficient here is 1, the leading coefficient here is 1. So we're going to get y equals to 1 is the horizontal asymptote. All right, over here, the degree of the numerator, n is 2, m is 1, n is greater than m, so in this case there's no horizontal asymptote. There's none. All right, right here. The degree of the numerator is 2, the degree of the denominator is 1, n is greater than m. Also in this case, there is no horizontal asymptote. That's what we know about that. There is a however case. However, the however case, however, if n is 1 more than m, an oblique asymptote exists. And you can find an oblique or a slant asymptote by division. So let's see. We said there was y equals 0 was a horizontal asymptote. And we said y equals to 1 is the horizontal asymptote. And here we said there's not a horizontal asymptote, but n is 1 more than 1 m. So right here, I'm going to say an oblique exists. We're going to go find it. No horizontal asymptote, but an oblique also exists here. Oblique exists. Okay. If, let's just say n was 3. Pretend like n is 3 and m is 1. N is greater than m, so there's no horizontal asymptote. N is not 1 more than m, it's 2 more than m. Then we would say there are no obliques either. That's what would happen in that particular case. All right, we're almost ready to graph these guys. Let's go through. I just want to do case number 4. It's kind of a special case. We're going to do case number 4, and then we will go back and graph these others. So, number 4. I'm going to erase this stuff. We already said that. We said, okay, we decided there's a hole at x equals -3 and that there's no vertical asymptote. And so what you're allowed to do is if you have a function, I'm going to go ahead and factor the numerator, where there is a cancellation. After you establish the domain, and we did, we said x can't be -3, and you make the cancellation. You say, okay, x equals to 3 is a whole. There's no vertical asymptotes. You and I are allowed to work with their simplified function. So let's just think about this. R of x is equal to x plus 3. I want to just think of this as y is equal to x plus 3. And when I look at that, that is not a rational function. That is a line. That is y equals mx plus b. So let's see. Y equals mx plus b. The slope is 1 over 1. The y-intercept is 0, 3. Let's graph this line. Okay? I'm allowed to work with the simplified function, understanding that there's a hole at x equals -3. So how I like to graph a line is go to the y-intercept. Let's go up 3 and put a point. Let's rise 1 and run 1. Let's go up 1 and run 1, up 1, right 1. And so right here, this is going to be my line. This is my line. Okay, that would be great if it started in that form. It didn't start in that form. It started as a rational function. So this rational function, which got simplified into this form, had this domain issue at x equals to 3. So let's go over here at x equals to 1, 2, 3, 1, 2, 3, and where that meets the function up here, it's going to have this hole in it. It's undefined right there. This is the case. This is kind of a special case because in this case, this line basically is kind of the slant asymptote that you're seeing. So that's the picture of number 4. I'm going to erase it, and we're going to look at how to graph the other 3 in the next video.